Okay, so let's talk about gravitational potential energy. In the past, in secondary school, I believe you have learned that for gravitational potential energy, there will be mgh, right?
Yeah.
And the small letter g, what is the value of the small letter g there?
9.81.
Uh-huh. And then how are you going to call g? Like, what's the name of this small letter g?
It's like, I don't know. I don't know what they call it, like the
Mm,
gravitational field. Well, they call it the gravitational field strength of Earth, but like,
yes, yes, you are right. We call that gravitational field strength. And in fact, it has another name. It can also be known as gravitational acceleration. And now, if you look at the units for gravitational acceleration, I'm going to say that it is 9.81 meter per second square. And if that is gravitational field strength, I'm going to call that 9.81 Newton per kg. And now, do I need to show you that actually the meter per second square is basically the very same as Newton per kg? Like, basically, they are the same guy, they are the same guy.
Okay.
Okay. Now, one more thing is, for gravitational field strength, you are going to learn that the definition of gravitational field strength is force per unit mass. Force per unit mass, we call that gravitational field strength. All right. So now, today, we are going to tell students that GPE equal to mgh, right? It is actually applicable when the difference in the height between 2 points is very small. Are you okay?
Okay.
So
Okay.
now, have you ever seen something like this, please?
I think it's on my teacher's slide, but I wasn't there, so I haven't seen it myself.
Okay, so anyway, later on I'll have a few things for you to memorize. Okay, later on I have a few things for you to memorize. Let me check. Okay, there are basically 4 items that normally I ask students to memorize. The first one is gravitational force equal to negative gmm over r squared. The first thing, and then gravitational field strength is negative gm over r squared. Gravitational potential energy, I call it U. Okay, U, capital U. Gravitational potential energy, negative gmm over r. All right. And finally, we have gravitational potential. So basically, there are 4 items here. Okay, basically there are 4 items here. Let's come again. We have gravitational force, we have gravitational field strength, or you can call it gravitational acceleration. And then we have gravitational potential energy. Finally, we have gravitational potential. So basically, there are 4 items here. Have a look first. So far, still okay?
Yeah.
Don't worry, later I will explain to you like more in details, like who are they, all right? For
Okay.
example, the most common question that I got from students is, what is the difference between gravitational potential energy and gravitational potential? Gravitational potential energy is like the total energy of any kilogram of object. But gravitational potential is simply the gravitational potential energy for only 1 kg of mass, only for 1 kg of mass only. That is for gravitational potential.
Okay.
But it's okay. I don't think we're going to deal with that today. We are going to talk about that next time, all right?
Yeah.
Okay, so now the first thing we have to learn is the Newton's law of gravitation. Because due to this law, we are going to come up with gravitational force is equal to negative gmm over r squared. Yeah, you can have a look at this. And make sure that you understand I purposely highlight the word point, because this law is only applicable for point masses. If this is a volume of mass, then we cannot apply this anymore. Still okay with the fact that your force is directly proportional to the product of masses, and then inversely proportional to the square of separation. The separation means the distance between the 2 point masses, all right?
Okay. Okay.
Okay, so now, have you ever seen the capital G before? Capital G. Capital G is like a constant. It's like a constant, and the constant is 6.67 times 10 power 11.
Okay.
But to be honest with you, I didn't really memorize the unit because I know that I can always derive this from the equation, all right?
Okay.
Yeah, okay. After so many years, I still cannot remember the units here. I'm going to derive that from the equation. But I can remember the number 6.67 times 10 power negative 11. Okay, still good?
Yeah.
And also, do you still remember what is the Newton third law of motion? Newton third law of motion.
Oh, yeah.
That means for all the forces, there will be like action and reaction, right?
Yeah.
And the action and the reaction have opposite directions, but they have the same strength. Okay, they have the same magnitude. All right.
Okay.
And then, for your information, this is the Earth, and you know that the Earth is rotating around the sun. All right. And if you still remember, just now I mentioned that Newton's law of gravitation is only applicable for point masses, right? Isn't it?
Yeah. Point mass.
Yeah, but you see, oh my God, the sun is so huge, the earth is so huge, all right? Then, why Newton's law of gravitation is still applicable here? I thought these two objects, I mean, I'm referring to the sun and the earth, are supermassive, isn't it? The thing is, the distance between the earth and the sun is so crazily huge. And the distance between the earth and the sun is like basically much, much, much larger than the radius of the earth and also the radius of the sun. Are you okay? So if you zoom out, like imagine if you are the God, okay, if you are God, from your perspective, you will really say that, oh, from my point of view, the earth and the sun, they really look like point masses though, because the distance between them is crazily huge compared to the size of each of them respectively. Are you okay?
Yeah.
So
Okay.
due to this fact, now you see, did you know that the distance between the sun and the earth is basically 1.5 times 10 power 11 meter? Because if you are curious in astronomy later on, we call it AU, astronomical unit. So basically, this is the average distance between the sun and the earth. And you know that the radius of the earth is so small, the radius of the sun is so small compared to the distance between them. And that is why we can safely say that The sun and the earth are simply point masses. Okay?
Okay, yeah, it makes sense.
And remember, mathematically, we are going to put double arrow, you know. I'm not going to say that distance is larger than radius of the earth. I'm going to say that the distance is much, much, much larger than the radius of the earth. Are you okay?
Yeah. Okay.
Okay. Because you are taking AQA A level, I'm not sure if this keyword is too important for you or not. But at least for A level, the word much is necessary. All right. For Cambridge A level, the word much is necessary.
Okay.
Okay. And also, do I need to tell you that in circular motion, your force is perpendicular to your velocity, because your velocity is a tangential velocity, by the way, and therefore the gravitational force does not do any work done onto the earth, and which is why the earth is going to move around the sun at a constant speed. Like you can imagine that it does not get faster and faster and faster again. All right.
Okay, yeah.
Because still remember, right? Work done is force times distance in the direction of the force. Okay. So when your force and velocity are 90 degrees, basically you didn't do any work done. All right.
Okay.
Okay. Okay, so you know that the reason why the Earth can rotate around the sun is because of the gravitational force. Gravitational force provides centripetal force. All right, gravitational force provides centripetal force. Or in simpler English, we can simply say that gravitational force is exactly the centripetal force. They are the same guy. All right.
Okay.
Okay. Do you know that if there's a circular motion, you must need a centripetal force so that it can complete a circular motion, right?
All right, yeah.
So you know that the function of centripetal force here is just to change the direction of motion continuously, all right? Okay. Now in a circular motion, can you say that the point mass has a constant speed? Is that okay? Can you say that the mass has a constant speed in the circular motion?
Yeah, constant speed.
But can you say that the mass has a constant velocity in a circular motion?
No.
Why? Because
It changes directions.
all right. So since your mass does not have a constant velocity, that's why you need to have a acceleration here, and that's why you need a net force here. And the net force is known as centripetal force, which is towards the center of the circle. All right.
Yeah.
Okay, so now do you know omega equal to 2 pi over t?
Yeah.
And the capital T is the period. All right. Okay. And you know, let's say this is a fan. Okay, this is a fan. This is a rotating fan. Now, point A is basically at the edge of the fan, and point B is like somewhere at the midpoint of a blade of the fan. All right. So now, if this is a rigid fan, okay, can you imagine this is a fan, you know, rotating fan?
Yeah.
When point A has finished a complete circle, point B also has finished a complete circle, right?
Yeah.
Meaning that both of them take the same time to complete an oscillation, isn't it?
Yeah.
And meaning that both of them have the same period.
Yeah.
Do you still remember period is like the time taken to complete one oscillation?
Yeah.
Okay. And now, did you know that period A equal to period B? And that is why omega A equal to omega B. By the way, omega is angular frequency, yeah? All right?
Yeah.
But now I'm going to do one experiment. I'm going to put my finger, okay? I'm going to use my finger to touch point B and also touch point A when the fan is rotating. And do you think which point that my finger will feel more painful? Like, can you imagine the fan is rotating, and then as a naughty child, I'm going to use my finger to touch the point. All right. At which point A or point B, that my finger will feel more painful?
Point A.
Why?
Because it has, I don't know whether to say it has like a greater, uh, greater speed, I guess.
Yes,
Greater
yes,
speed
yes,
covers more
yes.
distance in the same time.
Exactly. Point A has a greater speed. All right. Even though point A and point B have the same angular frequency, but they have different speed. Okay. Okay,
Yeah.
you're right. Okay. Now, do I need to introduce you to the centripetal force? I think you are okay with that, right? mv squared over r, or maybe
Yeah.
omega squared. And actually, there is one more formula, mv omega, but that is super rare. I almost didn't see this in any of the textbook. All right.
Okay. Yeah.
mv omega is like too rare, very rare, super rare. All right. Okay, fine. This page is so important because they are going to tell you something about Kepler's third law. Now, let me ask you a very quick question. This is the sun. Now, this is the earth. And you know that the earth is making, a complete circle around the sun. And let's talk about, let's say, Jupiter. Jupiter is a bit further away from the sun. Now, do you think that both the earth and Jupiter take the same value of, same amount of time to complete one circle?
Uh,
Or maybe which one will take a longer time, in your opinion?
mm, Probably Jupiter.
Probably Jupiter is going to take a longer time, right?
Oh, I forgot. They're not aligned. Uh, yeah, I just assumed Jupiter.
Because just now when we were talking about the rotating fan is solid fan. So we know
Yeah.
that we know that both point A and point B will take the same time to complete one circle.
Yeah.
But this is about our solar system. And you are right. Jupiter is indeed taking a longer time to finish one revolution. All right. And in order to answer that in physics, we are going to use some formula. Okay, fine. You know that gravitational force is gmm over r squared, right?
Yeah.
Because that is the so-called what the Newton's law of gravitation. And you know that this gravitational force is the same as the centripetal force. So I give you some time, you have a look at the derivation. You know that your period square is directly proportional to radius cube. So indeed, the larger the distance, the larger the radius, then the longer the period. Have a look.
Okay, makes sense.
Okay, so you know that G is a constant because it has a value of 6.67 times 10 power negative 11, which is always a fixed value. Mass. Oh, by the way, did you know that capital M? Okay, now tell me, what is the difference between capital M and small letter m?
That I actually don't know. I don't.
Okay. Just now when we were talking about Earth, right? We are going to use small m for the mass of the Earth. Capital M is for the mass of the object at the center, which is not moving.
Okay.
I repeat that. Let's forget about Jupiter first, can we? Let's simply forget about that first. We know that the Earth is rotating around the sun, not the other way around, right?
Yeah.
So the sun is bigger. Let's use a capital M for the mass of the sun, and let's use a small letter m for the mass of the Earth.
Okay. Okay, so far so good. Yeah, so far so good.
Okay. Let's have a look at this. Okay.
Yeah.
Okay.
Makes sense.
Now, in order to ask students to remember this formula, right, I have to tell them that, you see, for period 1, 2, I mean capital T, let's look at capital T. Okay, so there are 2 here. And let's talk about R. 1, 2, 3. Okay, so 3, all right. You get me?
Yeah. Okay. Okay.
Okay, I mean, I don't want students to tell me like, oh, T cube is directly proportional to R squared. No, no such thing, please.
Okay.
Okay,
Yeah.
Okay, fine. So, now student might ask me, like, fine, what's the importance of learning this? T squared is directly proportional to R cube. Well, if I tell you the radius of the Earth is 1.5 times 10 power 11 meter, and the radius of the Jupiter, okay, by the word radius, I'm actually referring to the distance between the Earth and the Sun, and also the distance between Jupiter and the Sun. All right.
Yeah.
So
Okay.
we know that the Earth takes 365 days to complete one circle. What about Jupiter? Like, how many days does it take for Jupiter, to complete one revolution? Oh, well, we can do something like this. Have a look.
Yeah. Okay. Makes sense.
Okay. And now the orbital velocity. Orbital velocity is like the speed of the moving object around a circular motion. All right, that is the speed of that object. All right.
Okay.
So you know that the orbital velocity is square root g m over r, meaning that if the planet is further away from the star, then the orbital velocity must be slower. Are you okay? For
Yeah.
example, the Earth is moving really fast, the Jupiter is moving a bit slower. And let's say the Pluto is moving so slow. All right.
Okay.
And for example, let's say Mercury, Mercury is moving so fast around the sun. All right. Okay. Huh?
Okay.
Okay. So now, have you ever heard of escape velocity? Please, escape velocity.
No, but I can assume it's when it stops orbiting, like goes off orbit.
It's okay. So let's say, do you play tennis or do you play
Yeah.
basketball? Whatever, just whatever.
Yeah.
Okay.
Yeah.
Now you are on the Earth. You are holding on a, let's say, basketball, tennis, whatever. I don't care, just a ball. And have you ever wondered that if you really want to throw the ball, such that the ball will simply leave the Earth, like it's not going to fall down again, like you simply throw the ball like so fast enough that the ball can simply escape from the Earth. All right. Then what is the minimum speed you are going to throw this object away so that it can say goodbye to the Earth forever? Then you have to use this. Your kinetic energy must overcome the gravitational potential energy of the object so that the object can escape forever. All right. Okay. So you see, the kinetic energy half mv squared is
Yeah.
equal to gmm over r, the gravitational potential energy.
Yeah.
So you are using this formula to figure out what is the minimum velocity you are going to throw the object so that it can go away from the Earth forever. Okay.
Okay.
And remember, your escape velocity is square root 2 gm over r. All right.
2gm over r.
That's the reason why I asked you to remember this.
Okay then.
Okay. So now I want you to look back at this. The red one is orbital velocity, like the speed at which you are making a circular motion. All right. And the escape velocity is like the minimum velocity you need so that you can escape from the gravitational pull of let's say of the Earth forever. All right. And the expressions, they really look alike, except for there's a factor of 2 in the middle there. All right.
Okay. Yeah.
Okay, so far so good. Okay, so now let's talk about geostationary satellite. Are you okay? Geostationary satellite. Oh, by the way, which country you are in now?
I'm in Bahrain again.
Oh,
No,
okay. Now,
no.
if you are near somewhere around the equator now, then then only you have a chance to have got geostationary satellite here. Because okay, by the way, you know what is geostationary, right? Stationary, it means it's not moving, right?
Yeah.
By the word satellite, did you know that satellite refers to an object which is rotating around another object?
Yeah.
So isn't that quite, contradictory? You told me satellite must be something like rotating around another object, but then stationary. It's because like this. Okay, let's say Tevin, you are now, let's say, in somewhere around the equator now. All right.
Okay.
This is your house, and then you are standing here on the ground. If you have eagle eyes, you are able to see that, oh, there's a satellite there. And according to your opinion, day or night, like, in 24 hours, you keep on observing the same satellite. You realize that the satellite does not even move, like, 20 hours, let's say 8 hours have passed, 16 hours have passed, and the satellite is still there. It's still at the same spot in the sky, be it day or night. So that is why, according to this person living on the earth, they believe the satellite is not moving. Are you okay?
Yeah.
So that's why we call it geostationary satellite, all right?
Okay.
Okay, so now there are 4 conditions for you to have a geostationary satellite. Have a look here. The orbit must be circular. It cannot be ellipse. Okay, it cannot be elliptical. The period must be 24 hours, like exactly 24 hours. Because when your Earth has made a rotation, then self-rotation, then the satellite also has made a circle around the Earth. All right. And the satellite must be orbiting from west to east, because your Earth is spinning from west to east also. And finally, it must be above the Earth equator. Okay, 4 conditions for geostationary satellite. All right, please remember.
Okay.
So you can imagine there are some countries, if you have got geostationary satellite, the same satellite will always be above the same country, forever. All right.
Yeah. Okay.
Okay. Oh, by the way, did you know that why the Earth is rotating around the sun, like not the other way around? Like why the sun is not rotating around the Earth?
Because of the mass or the weight of the sun is bigger than Earth.
So the bigger the mass, right? Okay, it seems like what, like let's say a fat guy. Normally, a fat guy will be too lazy to do the work, right?
Yeah.
Okay, I'm so sorry. I believe, we have we have a big variety of human races. I believe this is not applicable to 100% of all human beings, but that is the general rule of thumb. All right, like
Yeah.
normally a fat guy would be too
Yeah.
lazy to move around, and then a slim guy, oh, he is so energetic, like going here and there, traveling here and there. All right. And the same logic applies to this circular motion. The heavier you are, the more reluctance. You have more reluctance to move. Okay. Okay. So now, yeah, have a look at this. The mass of the Earth is much, much, much smaller than the mass of the Sun. So that is why it's the Earth rotating around the Sun, not the other way around. All right. Okay.
Okay.
In another case, okay, for your information, this one, mass 1 is less than mass 2. Just now, I mentioned that mass 1 is much, much, much less than mass 2, okay?
Okay. Yeah.
But this is just less than. If your mass 1 is less than mass 2, that means actually both the mass will rotate around center of mass, like both M1 and M2, they are having their own respective circular motions, all right? Like
Yeah.
if M2 has a larger mass, then M2 will be moving in a smaller circle. And M1 is lighter, so that's why M1 will have a larger circle.
Okay.
And you know that they're like playing hide and seek, you know. How do I say? Like for example, let's say M2 is here. Let's say M2 is here. I'm pretty sure that M1 will be here. Are you okay?
Yeah. Okay.
Like you imagine that. You imagine that these two people are like how do I say, like they are playing a game. Like let's say M2 wants to catch M1, and obviously M1 wants to escape, right? Wants to stay furthest away from M2. All right. So when M2 is here, let's say M2 is here, I believe M1 must be here because they have the same period. All right. They have the same period. I mean, M1 and M2 have the same period and they have the same omega. All right.
Yeah. Okay.
And you know that M1 has a greater speed, M2 has a lower speed. Okay,
Yeah.
M1 has a higher speed, M2 has a lower speed, all right? Okay, and did you know that this center is the center of mass between the two objects here?
Makes sense actually.
Finally, if both of them have the same mass, then both of them will share the same circle. And obviously, we don't have to, I mean, according to the story just now, we don't have to worry that the two objects will collide because they will try to maximize the distance from each other in a circle, all right? They won't collide, all right?
Okay.
Okay. Okay. Have a look at this. Like normally, fatter guy will be lazier, so the larger mass will be in a smaller circle, and the small mass will be in a larger circle, all right?
Largest now. Okay.
And if you are super duper heavy, that means you are basically not moving because you are too heavy already. So far so good. Okay. Have a look at this. Okay, can I move on to gravitational field now?
Yeah, no problem.
Okay, so now please define gravitational field. Still remember I mentioned that gravitational field, gravitational field strength is force per unit mass.
Yeah.
Okay, and gravitational field is referring to a region where you are going to, a mass is going to experience a force. All right.
Okay.
And now, okay, let's talk about this. Let's say Tevin, you are 100 kg, okay? And let's say I have 50 kg, all right?
Okay.
Both of us will feel the same gravitational field strength because the gravitational field strength only depends on the mass of the Earth. it does not depend on our body mass. So that's why I don't care what's the value of your body mass, you are going to feel the same gravitational field strength, which is 9.8 Newton per kg, all right? And I hope you still remember that gravitational field strength is the very same as gravitational acceleration, all right?
Okay.
So you see the formula here. Just now you agree that the gravitational force is gmm over r squared, right? And
Yeah.
and obviously the capital M is the mass of the Earth. Small letter m is the mass of your body, all right?
Okay.
And do you still remember weight? Okay, weight, the gravitational force, W equal to mg. Still remember? I mean,
Yeah.
W equal to mg. Like long time ago, when you learn something like, let's say, force diagram. So let's say there is a person standing here. So we say that there is a weight coming down, W equal to mg, and then there is a, there's a normal force, normal reaction force from the ground, all right? Still remember W equal to mg?
Yeah.
So this is how we derive G equal to negative Gm over R squared, all right? Can I?
Yeah. Can.
Okay. Okay, so now you can check. In the past, you have been taught that G must be 9.8 something. But then at that time, you didn't really understand why do we get such a value. So today, if you use G equal to negative Gm over R squared, you are able to get the G equal to 9.81 here. And like I said, Newton per kg is the same as meter per second square. The two units are basically the same guy.
Okay.
Okay. Okay, now let's say we are now living in a compartment, all right? So let's say John lives at ground floor, Peter lives at third floor. Can we say that John and Peter feel the same gravitational field strength? The answer is yes, definitely. Because the difference in height between the ground floor and the third floor is so much less than the radius of the Earth. So basically we say that, oh, the change in height between first floor and the third floor is like nothing. All right, it's like nothing compared to the radius of the Earth. Okay, and let's look at this. Radial gravitational field lines are almost parallel on the Earth's surface. Okay, look at this line. Radial gravitational field lines are almost parallel on Earth's surface. What do they mean? It's like this. Did you know that gravitational field strength look like this? Yes or no? Like if I ask you to plot, gravitational field lines, it looks like this.
Okay then.
I mean, it's like what, it's like the electric field lines. I mean, in secondary school, I'm pretty sure that you must have learned something like, please draw the electric field lines, please draw the magnetic field lines, something like that, right?
Yeah.
Gravitational field lines is just like the same as the electric field lines of a negative charge, So that's why the arrows are shooting into the mass, right? The
Okay.
arrows are shooting into the mass. And if you ask me why the arrows must be shooting to the Earth, because the arrow represents the direction of force onto any mass here. I repeat, gravitational field lines. Okay, the arrows represent the direction of force onto any mass. You know that any mass will be attracted to the Earth, right?
Yeah.
So now, if I zoom in, this one, I zoom in onto the Earth, then you will see the gravitational field lines look like this. Okay, have a look. This is what happened when I zoom in to the Earth. So you will see that, originally the field lines should be in radial direction, but once you have zoomed in, they all look parallel now. Okay. So this is what they mean by radial gravitational field lines are almost parallel on the Earth's surface. Can you understand it better now?
Yeah.
Oh, by the way, I need to tell you, like, have you learned that, like, the closer the gravitational field lines are together, then the stronger the gravitational field strength. And if the gravitational field lines are so far apart, then the gravitational field strength is very weak. Still remember?
Okay.
Okay, I mean it's the same story as like a magnet. So let's say if I have a piece of magnet, North Pole, South Pole, and I draw some magnetic field lines here. Okay, so okay. From north to south. Did you know that? The yellow color region has a very strong magnetic field strength compared to blue color region? Did you know that?
Yeah.
Because in yellow color regions, the magnetic field lines are so close together. In blue color region, the magnetic field lines are further apart. Okay?
Okay.
So that's why if I zoom in, both the green and yellow color region have the same, gravitational field strength because they have the same number of field lines per unit area. Okay.
Okay.
And in this case, the red color region has a stronger gravitational field strength because you see in the red color region, the field lines are so close together. But in the blue color region, the field lines are so further apart. Okay.
Yeah.
If you put any mass m1 here, it will move according to the direction of arrow of gravitational field lines. So that's why gravitational field lines will be always pointing down, because I believe everything will fall down, right?
Yeah. Yeah.
Okay, so now, conclusion is this. If you put M1 here, it will fall down to the Earth according to this arrow, isn't it? So that is why the conclusion is the arrows of gravitational field lines show you the direction of force or the acceleration acting on a small test mass. All right.
Okay.
And G equal to negative GM of R squared. So it should, okay. Gravitational field looks like the electric field of a negative charge. All right.
All right.
Now let's have a look at the drawing here. Okay, now please understand that if your gravitational field is going to the left, then the gravitational field strength is negative. If your gravitational field is going to the right, then your gravitational field strength is positive, all right?
Okay.
And also, help me to understand that if you are so close to the point mass, right, your gravitational field strength is pretty huge. I mean, it has a big value, okay? It has a big magnitude. But if you are so far away from the point charge, I mean from the point mass, then the magnitude of the gravitational field strength will be approximately equal to 0. Okay, as you are so far away from the point mass, all right?
Okay.
So let's look at this. We want student to produce this graph, you know, the graph below here. Have a look. Okay, first and foremost, when you are so close to the mass, obviously your value is like, wow, super big, you know, super big. The value of the gravitational field strength is super big, all right?
Yeah.
And as you are so far away, like really, really, really far away from the mass, then your gravitational field is like, it's like 0.
Okay.
Yeah. And one more thing is, let's look at this. Generally, all the arrows here are pointing to left or right.
Yeah.
So if the field lines are going to the right, that means they have a positive value, right?
Oh, okay.
If all the field lines are going, okay, look at this yellow color region. It seems like the arrows are generally pointing to the left, right?
Yeah.
So that's why the gravitational field strength is negative, no? Okay, you quickly ask me any question. Because later on the graph will be a bit more difficult as we go along.
This is fine for now.
Like remember, if the gravitational field strength going to the left, then negative. If gravitational field strength going to the right, then positive. And if you are so close to the point mass, then you have a crazily big magnitude, all right?
All right.
Can I?
Yeah.
I'm going to show you this now. Remember these 2-point masses here. There are 2 objects here. Okay, so you see, like for example here, all the gravitational field strength are generally going to left or right.
Generally going right.
So it will be positive or negative.
Going right would be positive.
Okay, now let's talk about, okay, maybe I should keep the highlight here first. Let's talk about yellow color region. Generally to left or to right.
Left.
So,
it's negative.
okay. What about blue color region? Generally left or right?
Right.
Okay, to the right. So that's why it will be.
Positive.
And then finally here in the purple color region.
It's left again.
So,
So it's negative.
okay. Now one more thing is, what happens at the green color there? Green. It seems like no lines are there, right? Is it?
Yeah.
Yeah, it seems like no lines are there. So that is why at this point, you are going to have a 0 gravitational field strength, all right?
Okay.
So that is why at this pink color dot, I'm just going to, I'm just going to give it a name. Can I call it, let's say point lambda? I mean, I just give it a random name, all right?
Okay then.
So at this point lambda, your gravitational field strength simply means no gravitational force, all right? Like if there is an object here, let's say if there's an object here, the star here will not actually feel any net gravitational force, because the gravitational force due to the capital M and the small letter m, they basically cancel out each other. All right. Okay.
All right. Okay.
And remember this, have a look. In exam, if they ask you to draw gravitational field lines, then you are going to draw this thing. Draw the gravitational field lines. However, if they ask you to sketch a graph to show variation of the resultant gravitational field strength of the 2-point masses, then this will be your answer. Okay.
Okay.
Okay. Now, yeah, I need to tell student that at that point, just because the gravitational field strength is 0, no wonder your gravitational force will also be 0.
All right.
Okay. Okay. Now let's talk about the Earth and the Moon. All right. Which one is heavier, Earth or Moon?
Earth.
Okay. Now Earth is heavier than the Moon. So please help me to remember the point where your G equal to 0, right? Will actually be further away from the Earth and it will be closer to the Moon.
Okay.
Okay, so help me to remember that now your Earth has a greater mass, right? No wonder the magnitude of the G at the surface of the Earth is so big, you know. Like here, you look at this is so high, right? Compared to here, right?
Yeah, compared to the moon.
Like this one, right? Is so high compared to this one, all right? All right.
All right.
Because you know that G is gm over r squared. So that's why the larger the mass, the larger the gravitational field strength, all right?
Okay.
And the moon has a smaller mass, that's why the moon has a smaller gravitational field strength here, all right?
Okay. Yeah.
And I don't think I need to tell you why this is positive, why this is negative, why positive, why negative, right? You already know, right?
Yeah.
Okay. So remember, this is already the net gravitational field strength, you know? Like this is the gravitational field strength due to both the Earth and the moon, all right?
Okay.
And okay, now you see this point, can I say that the distance between this point and the Earth is RE, and then the distance between this point and the moon is RM? Can I say that?
Yeah, okay.
And today you have been given the mass of the Earth, you have been given the mass of the moon, all right?
All right.
So if I say that the total distance between the Earth and the moon, okay, the total distance between the Earth and the moon is 3.84 times 10 power 8 meter. So this distance is referring to the sum of RE and RM together, all right? The sum of RE and RM is exactly 3.84 times 10 power 8 meter, all right?
Okay.
So is there a method for us to find out the distance from the Earth center where the resultant gravitational field strength is 0? That means at the point where your resultant gravitational field is 0, you know that the gravitational field strength due to the Earth is exactly equal to gravitational field strength due to the moon. That is why these two gravitational field strength will cancel each other, all right?
Okay.
And then there are some calculations here. Yeah, you can quickly have a look. Because you have to understand, hang on. If you're at this point, right, you feel like Earth is pulling you to the left. You also feel like the moon is pulling you to the right. So only when these two gravitational field strength cancel out each other, then only your net G is 0 at this point. Can you get the story here?
Yeah.
Okay, so you can roughly have a look at the calculation. Anything you want to ask me regarding the calculation?
No, should be okay.
Like mathematically, sometimes students are struggling here. Like they don't understand why you are changing Rm into D minus Re. Because today the question only wants us to figure out Re, right? The value of Re. And D is something that we already know. So that is why I want to reduce the equation until we only have one variable, which is Re. Like we only have one variable that we didn't know the value. Okay?
Okay.
And the thing is, mathematically, Re appears twice, right? Isn't it? Re appears twice in this equation, right? And remember that we want to find out Re today. So that is why we have to figure out a method so that Re can only appear once in the equation, all right?
Okay.
And of course, after we have got Re, if you want to find out Rm, of course, you can do some further calculation to get Rm, all right?
All right then.
Yeah, so today, if you have known the value of Re and Rm, you would realize what you know. You would realize actually Re is much greater than Rm. Are you okay? Like the value of Re is actually much greater than Rm, all right?
All right.
So that is why if I want to draw a very precise graph, because just now I show you this graph, right? But if I really want the graph to be more accurate, it should be like this. Like you know that seriously, this point is so much closer to the moon and so far away from the Earth. Okay.
Okay.
Can
All
I?
right.
Because this distance is quite big compared to this distance. All right.
Okay.
Okay. No? So okay. Finally, one more thing. Okay, give me 1 more minute. I'm going to finish this very soon. Given the distance between the Earth and the moon, right? Just now you know that the distance between the Earth and the moon is 3.84 times 10 power 8 meter, right?
Yeah.
Like on a night sky, I believe you can see the moon, right? Always, right? Let's say on a full moon night, all right? Do you think the distance between you and the moon right now, do you think this distance is huge enough or not? Like, do you think the distance between you, let's say you are now on a night sky, you look at the moon, do you think the distance between you and the moon is big enough or not? The answer is it is big enough, you know. And in fact, I want to tell you a more crazy fact. Like, given the distance between the Earth and the moon, right? Do you think you can squeeze all the planets here or not? Like you want to squeeze all the Mercury, Jupiter, Saturn, whatever. Do you think they fit in between the Earth and the moon or not?
No.
Because according to what we believe, right? Let's say maybe the student will say that, oh, come on, how could that be possible? The Jupiter alone is already big enough, right? Isn't it?
Yeah.
But surprisingly, come on, look at this. Read the news. All of the planets in our solar system basically fit in. Oh my God, they fit in the distance in between the Earth and the Moon. You know, all right. Like, can you imagine that on your left you have the Earth, on your right you have the Moon, the Moon that you always see on the night sky. Like surprisingly, you can fit all the Jupiter, whatever here. You know, seriously, Mars, okay, Saturn, you know, Neptune, whatever. You can fit in all of them here. You know. Isn't it surprising? I mean, that's quite surprising, right?
Yeah, it is.
So that is why the conclusion is, because the distance between the Earth and the Moon is so much greater than the radius of the Earth and the radius of the Moon. By the way, if I zoom in, you could see that I label the radius of the Earth here, right?
Yeah.
And if I zoom in, you could see that this is radius of the Moon. Okay. So do you believe that the distance between them is indeed so much greater than radius of the Earth and the Moon, all right? So that is why, yes, the Moon and the Earth can be really taken as point masses according to this diagram. Okay, according to this scale diagram, they really look like point masses. Like, seriously. Okay.
All right. Yeah.
Okay. So hopefully today, after this lesson, you have learned. I mean, you have understood gravitational force and gravitational field strength. In a deeper level. All right. On a deeper
All right.
level.
Yeah.
All right.
Thank you. Okay. Thank you.
Okay. Okay. By the way, since talking about the past year papers, the ESAT, right? Like,
Yeah.
if you have figured out the any way to get the past year papers or whatever, please let me know. All right.
All right. I will.
And I'm going to see you on this Wednesday as well, right? Same time,
Yeah.
right?
This Wednesday.
Okay. So I'm going to see you again. See you. Bye
All right.
bye.
Then see you. Bye bye.